Hello everyone, welcome to our presentation. We are Team 1022 from PIMA Projects in Mathematics and Applications, Hồ Chí Minh City. The team consists of me, Nguyễn Ngọc Canh, my teammates Hoàng Dung and Nguyễn Bach, and our coach is Phan Danh. Today we are going to talk about our approach to problem C, standing against the mammoth from the NICE SCUDEM Challenge in 2024. The presentation will cover 5 sections. We will introduce the problem, present a general model as well as a specific models for the two hunting methods, throwing spear and charging mammoth. Finally, we will simulate these two scenarios and answer the related questions. First, the introduction. Throughout history, early humans developed increasingly advanced tools to hunt large animals, such as the mammoth. One such tool was the cloven spear, which represented a major technological step forward. The cloven spear had a pointed stone head securely attached to a spear shaft. This design allowed hunters to inflict significant damage and have them manage the distance between themselves and their prey, an essential factor when facing large and dangerous animals. In terms of how the cloven spear was used, researchers suggest two primary methods. In the first method, hunters throw spear, allowing them to stay at a safer distance from the animal. However, this approach might have limited the impact force when the spear made contact with the prey. In the second method, the spear was braced or fixed in place, so that a charging animal would essentially impale itself on the spearhead. This approach likely creates a much stronger impact and increased the lethality of the weapon, though it requires hunters to remain close to the animal, putting themselves at a greater risk. Next, let's discuss the assumptions made in our modeling. First, to avoid overly complex calculations, we will ignore air resistance. Second, we assume that the spear will not bend or break in either scenario. For the scenario for the spear is braced, we consider the mammoth running speed toward the spearhead to be constant. Finally, the spear tip is considered as a point in the mechanical system. Our goal is to evaluate the effectiveness of two cloven spear hunting methods by building a mathematical model. We focused on two key questions. First, the impact comparison, determining the charging speed of an animal that would give a similar impact force to a throw spear, helping us understand energy transfer upon impact. Second, we examine the side factors of a spear to see how its shape and structure affect its use as a throw versus a prey weapon. Our model and simulations aim to determine which method was more practical and effective for early hunters.
Firstly, we're going to with a general model. At the first stage, before the collisions, we assume that elephant and people are standing at a fit distance from each other. And we use the dynamic model to describe it according to Newton's second laws. This is the formula. Next, the time of collisions. We focus on the collision energy. We use the arc-game model. Here, you can see that lambda is the strain ratio. And the larger L, the model becomes more complex. But to simplify, the problem we select n equal 1. And lambda 2 and lambda 3 equal 1. So this is the arc-game model with the n equal 1. The second thing we focus is the strain skin. We can see that it changes the length of the tissues compared to its original length. Here it is strain. Calculate the delta L, the change in length of steel. We can see that the arc-game model we use to calculate the kinetic energy. And we combine the lambda with the chain strength, and after that we can calculate the delta L here. If we have a delta L, we can calculate the acceleration. This is the more important thing at the time of collisions. Here we have a formula. It's derived from the relationship between the initial velocity and the change in the position during the collision event. After the collisions, the important thing we want to calculation is spread, because the part per unit area during the collisions is the spread. And when the spread exceeds the tensile strength of the skin or material internal the bone start to break. To calculate the spread, we based on the Maxwell model. The Maxwell model is the most simple model with elastic material. We can see that E defines the relation between the stress and strain. Here is the strength and here is the strength in the skin. Dedicates on the characteristic stem scale. Here, to analyze this, the strength equal delta L divided L. And if we derivative the strength, we have a velocity. Finally, we have this model with velocity. To post the collision velocity here. The second thing we care is relaxation. Because over time, the strength begins to decrease, even though the strength is maintained. And we can see that the friction relations depend on the strength and the time. GT describes the strength decay over time. For example, we can choose the potential and the strength response. We use the Maxwell this formula. So from this, we build our model strength development. We consider the influence compared to strength components. Yes, and we derivative the strength to have the velocity and have a strain rate. We derivative the stress. And after that, we have E. This is the constant. So the stress is directly proportional to the change in strength. And the last one is realization characteristic. The Maxwell model is not accurately describe the case of puncture into the skin, where the sharp object contacts the skin. So if we consider the local deformation and the stress realization, then we combine the stress equation. It's expressed as the interval to span the 0 to t. Here the stress is determined by the product three main components. The relation function, the present of derivative of stress with respect to strength, and the rate to strength over time. So we're substituting to our combined stress equation. So that we have, and using convolution provide a clear way to model stress response on the function, both material properties and the inward velocity. And it implies the importance to relaxation function and the time constant in determining the stress behavior. And in this function, we have to calculate initial velocity. Okay, we will prove that the velocity at the time of collisions is correct to both hypotheses. Relation at the time of collision we calculated before. Then, if we have a velocity, now we can solve the model stress. Here we can see that we can calculate in the interval in the time domain is so complex. But if we can calculate in the Laplace domain, next we define that f function equal exponential, and we use the Laplace transform series to know that. Second, the G total. This is a velocity, and also we use the Laplace transform. Finally, we combine this function to have. Then we apply to our stress equations with the Laplace transform, and the result here. But we want to calculate the stress at time. Then we introverse the Laplace transform for each component. We also use the series transformation. Finally, we have a solution here. It's combine the effects of exponential decay, the linear growth, and material properties. And we can see that the capture initially respond and its relations over time. The component here is accounted desolation effect. And finally, the residual stress dedicating is exponentially. This is our summary. Our summary table at before at the time and after the collisions.
In this section, we'll discuss the dynamics of throwing a spear at a mammoth using projectile motion. Here, we model the spear as a point mass, and we set the starting position of the throw as the origin. We break down the velocity vector into two component vectors, aligned with the x and y axis. The x component Vx equals V0 times the cosine of theta, where V0 is the initial speed given to the spear, and theta is the launch angle relative to the ground. And y component Vy affected by gravity is V0 times the sine of theta minus GD. By applying the Pythagorean theorem to the vectors of magnitude, we derive a function for velocity v as a function of time t. Using this function, we can also derive a function for force f as a function of time by differentiating v in line with Newton's second law. The graph of f is a curve with a single maximum point, helping us identify an ideal time for the problem. However, differentiating f precisely to find this maximum is complex, so we propose an alternative. Select a time t1 close to this peak, such that v1 is approximately equal to the initial velocity. From there, we can simply review results we have already demonstrated earlier in the video.
In conjecture 2, we assume that the sphere doesn't break and the mammoth will stop after delta t seconds from the moment of impact. The jet force of the mammoth will be equal to its mass multiplied by its running velocity divided by delta t. According to Newton's third law, we can deduce that the impact force is also equal in magnitude to the jet force. After the collision, we assume the mammoth's velocity decreases linearly with time. And here, tau r is the skin relaxation time constant. We check the velocity of the mammoth and we assume that it is constant. A, the acceleration, E, the skin elasticity, and L, the impact length. The stress sigma t is calculated as the formula you can see on the slide.
Let's move to the discussion. This is our simulation scenario. We can see that the initial velocity in Nguyen's rate is always higher than velocity in mammoth. And we can see that the kinetic energy is around 1033. But the spread peak is about 130. And when it's negative, not negative spread, it's about 254. And this is the simulation scenario when tracking the mammoth. And we can see that the initial velocity is 0 about 10. The kinetic energy is very high, but the spread is low. We can know that the lower impact energy and the higher strength is the mentor on the momentum. And effectively, it is the ideal for the large break. In another, we have a high impact energy, but the lower strength. The method used to raise the spray, where the weapon is fixed, and effective on a smaller target when the animal vulnerable in sport.
Next, we will address the question, what velocity must the mammoth have for the damage to be equivalent to that of throwing a spear? Assume the spear has a mass of 3 kilograms and an initial velocity of 30 meters per second, similar to the throwing speed of a professional javelin athlete. We will also assume that the spear collides with the mammoth at the end of its trajectory. In that case, the energy, specifically the kinetic energy of the spear, will be 135 joules over impact. If we assume that the damage to the animal depends entirely on kinetic energy, then for an energy of 135 joules, a mammoth weighing 7 tons would need to run at the speed of 0.2 meters per second. Meanwhile, for the stress caused by the spear to be the same in both cases, the mammoth would need to run at the same speed as the spear at the moment of impact, which is 30 meters per second. In reality, elephants today can run at a speed of 10 meters per second, and the speed of mammoths were probably around the same.
And finally, we have the question of comparing the shape of the spear in two different uses. Clearly, a throw spear is affected by air resistance, so we need to design its tip with an asymmetric or streamlined shape to optimize aerodynamics. However, a braced spear should have a tip that starts with a small contact surface and then gradually widens towards the shaft to create a larger valve opening and enhance durability. Comparing this with the clovis point used by early humans, we see that the spearhead has a flatter, more horizontal shape. This strongly suggests that early humans prefer hunting mammoths by throwing spears rather than standing in place, likely to avoid the risk of being jacked and killed by the animal. And that's what the last of the video. Thank you for listening.